physics kids, this is the second part of magnetism, and in this one what I want to talk about is magnetic fields when you're having a current in a wire. A current in a wire causes a magnetic field. I'll link a Veritasium and minute physics video that explain this much better than I can. Suffice to say that when you have a current flowing through a wire, you create a magnetic field in concentric circles, not spirals, but rather concentric circles around that wire. What I'm going to show you today is simply the conventions as how to figure out where that magnetic field goes, and these are called the left-hand rules. Now, if you get to college, you might find that your professor is talking about the right-hand rules. What the heck? Well, when Ben Franklin came up with positive and negative to describe electrical flow, there was no way to tell which way electricity was actually flowing. And he guessed, and in this case, Ben guessed wrong. So, we have always had negative terminals and positive terminals. Normally you'd think things would flow from the source, the positive, over to the sink, the negative. Well, later on when we found out what was really going on, instead of swapping it, we just dealt with it. So you'll hear sometimes something called conventional current. Conventional current is the way they used to think it went. They used to think positive to negative. Now, it rarely makes any difference in any situation, but if you hear conventional current, you'll be using the right-hand rules. I figure you're starting off, why don't we just make sure we're understanding what's really going on, and that is the flow is from the negative terminal to the positive terminal. Electrons, the negatively charged electrons, they're the ones flowing. So we will be using the left-hand rules. The left-hand rules then describe what's going on in actual current. Conventional current, you get the same results, just need to switch hands. Okay, so the first left-hand rule, we're talking about straight conductors. And here we have the negative part, positive part, and we know electrons are flowing along it like that. So how do we describe the magnetic field wrapping around it? Well, we use our left hand. Make sure it's your left hand. That's going to really help. The first left-hand rule says grasp the conductor with your left hand. Now, I'm not suggesting you grasp a live wire with your left hand. That might be bad. It's not any better with your right hand either. But in this theoretical experiment, if this is playing the part of the conductor, and I grasp it with my left hand. Now, the fingers are pointing in the direction of the magnetic field. Well, how do we define the magnetic field again? Well, the way a compass would point. So if my fingers are grasping it, the key is left-hand rule. Thumb is pointing in current flow. And if you have your thumb pointing in the direction the current is flowing, and you have your fingers grasping the conductor, your fingers show how the magnetic field wraps around that conductor. So in this case, you can see my fingers on top are pointing into the board. My fingers on the bottom are pointing out of the board. So the convention X marking in, O marking out. So we would say the magnetic field is going into the board there. It's coming out of the board on the bottom. And that's very simply how we define the magnetic field around a straight conductor. Okay, what can you do with that? Not much. Why? The magnetic field is incredibly weak. But if you were to take that straight conductor and we have the current flowing this way, if that conductor was to be wrapped in a coil, well, now look at this. This is the way the current is flowing, and all around the inside, the magnetic field is flowing the same direction. Everywhere inside this coil, the magnetic field is flowing the same direction. So if I were to make lots and lots of loops in that coil, I'm going to have a very strong magnetic field. Furthermore, if in the magnetic field I were to put some sort of iron bar, even though that is not a magnet, it has domains in it. And if I run current then through that coil around that magnetic bar, I'm going to turn that entire magnetic bar into a very strong electromagnet. Okay, so that brings us to the second left-hand rule. The second left-hand rule says, now, fingers in current flow direction So if you have the fingers in the current flow direction, now your thumb will point in the direction of the magnetic field. Take a look at this. Here we have two coils drawn on the board. In this, we have the negative, and it wraps around behind. So here, again, making sure I have my left hand, we know the current is flowing in this direction. My fingers wrap around that in direction of current flow, and I know the north end is on the bottom, the south end on the top. But you can never just assume because it's negative that that means the south end is on the top, because you could wrap the coil, obviously, the other way. So this way, it's wrapped the other way, and if my fingers, the current is flowing this way, if my fingers wrap around it, now my thumb is pointing up. The north end is on top, the south end is on the bottom. So when you have a coil, for example, like this, hooked to a battery, if I connect the other end of the battery to this, and I don't want to do this long because after all the coil is a conductor and I'm kind of shorting out the battery, so we don't certainly want to do it for too long. But notice this, which is just part of a screwdriver, an iron bar, is not a magnet. But if I put that in the middle of the coil, now the coil causes the domains of it to line up, and you can clearly see it's a magnet now. Make sure you disconnect that coil. You can feel the whole thing getting hot a little bit. So coils then become extremely important. They can become such potent magnetic fields when you run electricity through them. This would be the coil of a heavy-duty motor. And with this iron around it, you can imagine this becomes an extremely powerful electromagnet when you throw current through this coil. It becomes extremely powerful. When you have the internal workings of it, that will turn so hard that your hands couldn't stop it. That's a really powerful electric motor. Let me grab another one here for you. Couple other examples. Here we have the actual armature. We have all the functions of the electric motor. This is from an old drill. And you can see a lot of coils inside. Turn this into an extremely strong electromagnet. A lot of coils plus the iron. You can see the iron there too. Make both of these very strong electromagnets. You can get them to repel each other and spin this. That is how an electric drill works. But a lot more things use coils than you might first suspect. This is a speaker torn apart. Don't ever lend me a speaker. On the back of it is a very strong magnet, right? Very strong magnet. How does the speaker work? Well, I ripped this out of the speaker. It usually sits right in the center and there's paper attached to it, but rip this out, and if you look closely, that's a coil. So when I speak into a microphone, it's the same thing. There's a coil in there. My voice causes the paper to vibrate the coil. That makes little tiny electrical signals. If we amplify them and send them to a speaker, when those electrical signals at the particular frequency of my voice go into this coil, it causes the coil to become magnetized. As you increase its magnetism, it's pulled in towards that magnet. It goes inside. Then you reverse that, and it goes out, in and out, and in and out. If I have the right frequency, it will simply pick up what I'm doing into the microphone, the electrical signals going into the microphone, and replicate them on the speaker. That's how a speaker works. It's a coil and a magnet. So that you will find coils all over the place in so many different devices, because what they do to magnetic fields is truly incredible. And we don't worry about the magnetic field on the outside of the coil because it's too dilute. Everything is about the inside of the coil, because that's where the magnetic field gets truly strong. So that's the first two left-hand rules. First left-hand rule, again, thumb points in the direction. This is the independent variable. Thumb points in direction of current flow. Fingers wrap in direction of magnetic field. Second left-hand rule, now the fingers wrap around the coil. This is all about coils, the second left-hand rule. The fingers wrap around the coil in the direction of the electron flow. The thumb now points to the north magnetic field, the direction the magnetic field is coming out of the coil. So that's the first two left-hand rules for you. Hope you got it. Hope I made sense there. Thanks for watching.